This question is about organic compounds containing nitrogen. Part A. Salt H, CH3, 2, CH, NH3, Cl is used in the manufacture of garden weed killers. The flowchart shows the synthesis of the salt H from propanone. Complete the flowchart and show the structures for organic compounds. So let's start by drawing propanone. We have a 3-carbon backbone, and then we have CH3 as our 2 R groups and a double bonded oxygen, so a carbon R group. When you react propanone with NaBH4, this is a reducing agent and it's going to undergo nucleophilic addition. So that's when this carbon R group is turned into an alcohol group. So if we draw this structure out, we have CH, we still have our CH3R groups, but then instead of this carbon-oxygen double bond, we have an OH group. Then we need to look at the reagent of going from this alcohol group to a bromine. So this is nucleophilic substitution. And your reagents are NaBr or just Br-, so that's your nucleophile. And then you need H2SO4 or an acid to help with this nucleophilic substitution. The acid acts as your catalyst. Then we need to look at the next step. So we don't have any clues, but we do have this final salt product. So firstly, before we get to this salt product, we're going to have an amine formed. So that's going to be CH, NH2, and then we have our 2 CH3R groups. So the reagent to go from this haloalkane to an amine is NH3 and ethanol. Alternatively, you could have said that you're going to use an excess of NH3 or ammonia. Then finally, we need to look at the reagent to go from this amine to the salt. So we look at what we're missing. Well, we're missing a hydrogen and a chlorine. So our reagent is going to be hydrogen chloride. To get the 5 marks for this question, you get a mark for each reagent that you've written, and then you get your other 2 marks from the 2 structures that you draw. Part B. Aspartame, shown below, is an artificial sweetener commonly used as a sugar substitute. Part 1. Aspartame contains several functional groups. Apart from the benzene ring, name the functional groups in aspartame. So if we start working from left to right, our first functional group is here. And this is an ester functional group, which we can bullet point in this question. Then moving along, we have this amide functional group. So in the question, you don't get marks for classifying if it's primary, secondary, or tertiary, but just for consolidation, this is a secondary amide. It would be a primary amide if you had NH2 here, and it would be a tertiary amide if you didn't have a hydrogen here. Then if we move along, we have this NH2 here, and that's an amine. So an amine means it doesn't have a carbon R group, so it doesn't have this carbon double bonded oxygen. And this is a primary amine. So to make it secondary or tertiary, you need to get rid of these hydrogens. Then if we look at the last functional group here, we have a carboxylic acid. So the way marks are awarded for this question, it's not 1 mark per functional group correct. Instead, 4 groups correct will get you 3 marks. If you've got 3 groups correct, you get 2 marks. And if you've got 2 groups correct, you get 1 mark. Part 2. A sample of aspartame is hydrolyzed with aqueous acid. Draw the structures of the 3 organic products of the complete acid hydrolysis of aspartame. So acid hydrolysis is when you're going to react with H+ and break some bonds. So the bonds that are going to be broken are this ester bond and this amide bond. So when you break your ester bond, you're going to form an alcohol and a carboxylic acid. And when you break an amide bond, you form an amine and a carboxylic acid. So starting with the ester group first, breaking it and forming the alcohol, we're going to form methanol. So CH3OH is our first structure. Then if we draw the carboxylic acid and the amine, so we're going to have our benzene ring at the bottom, and then the rest of the structure is the same except we're going to have NH2 and then our carboxylic acid. So making sure everything's the same by drawing the ring in the benzene ring. But because this is acid hydrolysis and you're going to have an excess of H+, what's going to happen is the NH2 is going to be converted into NH3+. Then we need to draw our last structure, so we're turning this into a carboxylic acid at both ends. So we're going to have HOOC, and then our carbon backbone, COOH, and our NH2. But again, because we've got this excess of H+, this NH2 is going to turn into NH3+. And to get the 4 marks for this question, you get your marks for each of the structures, so 1 for each structure, and then your 4th mark comes from remembering that the NH2 groups are going to be converted into NH3+ groups. Part 3. Some people are concerned that aspartame C14H18N2O5 may have adverse health effects. Research shows that the safe maximum daily intake of aspartame is 1.7 times 10 to the negative 4 moles per kilogram. A typical UK adult has a mass of 75 kilograms. A can of a diet drink contains 167 milligrams of aspartame. How many cans of this diet drink is it safe for a typical adult to drink in one day? So firstly, let's highlight the key pieces of information in this question. So that's going to be the molecular formula of aspartame. That's going to be the maximum daily intake of moles per kilogram, the average mass of an adult, and the milligrams of aspartame that a can contains. So the first equation triangle and the only equation triangle we're going to use in this question is mass is equal to moles times relative formula mass. So we're going to have mass at the top, moles, and then relative formula mass. So working out the relative formula mass of aspartame, that's going to be 14 times 12 plus 18 plus 2 times 14 plus 5 times 16, which equals 294 grams per mole. So now we're going to use this equation triangle to work out the moles in 1 can. So the way we're going to work this out is milligrams divided by relative formula mass will give us moles. So 0.167, so that's milligrams divided by 1,000 to get grams. And then we're going to divide by 294, and that equals 5.68 times 10 to the negative 4 moles in 1 can. Now we need to work out the number of moles per day. So that's going to be 1.7 times 10 to the negative 4 multiplied by 75. So that's using the units of moles per kilogram and then multiplying by kilogram to just get moles. And this equals 0.01275 moles per day. So to work out how many cans you can have in a day, we're going to do 0.01275 divided by 5.68 times 10 to the negative 4. And this equals 22.4 cans. But you can't have 0.4 of a can, so the number of cans that you can safely drink is 22. Because if you have 23 cans, that's going over 22.4 and therefore over the safe amount to drink in a day. To get the 3 marks for this question, you get a mark for working out the number of moles in 1 can, so 5.68 times 10 to the negative 4 moles. You get a mark for working out the number of moles you can have per day of aspartame, so 0.01275 moles. And then you get your third and final mark for working out how many cans you can have, so this is 22.4 or 22. The mark scheme will also accept 23, but it's better to put 22 or 22.4 because these are both within the limit and the actual safe amount that you can drink in a day.